Good afternoon. Welcome to Minimum Failure, Stealing Bitcoins with Electromagnetic Fault Injection in Lagoon JKL with Colin O'Flynn. Before we begin, a few brief notes. Please stop by the business hall located in Mandalay Bay, Oceanside, and Shoreline ballrooms on level 2 during the day, and for the welcome reception at 5:30 p.m. tonight, right after this talk. The Blackhead Arsenal is in the business hall on level 2. Also, please join us for the Pony Awards in Lagoon JKL at 6:30 p.m. in this room. Thank you for putting your phone on vibrate as well. It makes it easier for the rest of us to ignore the ringing. Colin, it's all yours.
Thank you very much for that introduction. My name's Colin O'Flynn, and I'm going to be talking to you about stealing Bitcoins with electromagnetic fault injection. So I sort of do two different things. Part of my life is with a startup I have called New AA Technology Inc. And this is spun out of an open source project I started called Chip Whisperer, which does side channel power analysis and fault injection. So there's a lot of open source software and hardware involved in that project. I have some here with me. I also work at Dalhousie University in the east coast of Canada, Halifax, where I also live, as an assistant professor working on research in the area as well as with local embedded startups. All right, so why are you here? The last talk of the day, you really want to be at the welcome reception, but you sat here. So I'm going to give you, as a reward, a true history of blockchain, me gambling with a third of a Bitcoin, physical giveaways, attacking Bitcoin wallets and stealing things, bonus content, which isn't in the abstract at all, crass commercialization, an open source tool release, and fixing your crappy code in 25-ish minutes. All right, so blockchain. So this talk doesn't really focus on blockchain, but a brief background maybe helps understand why it's useful and what's the interest here. So blockchain you can sort of split into two things. You really have, number one, the first half of it would be your block. So this is like the concrete masonry unit, CMU. This is a North American standard block. And you also have a chain. So depending on the security you need, you could change the chain strength. This is a number 4 straight link chain. And so blockchain is really powerful because you have an issue like, voting booth, electronic voting booth needs to be secured. So what you would do is you would have a block here, for example, and then you would have a chain. And that's pretty good, but the real power of blockchain comes in the fact that you can combine multiple of them, right? So now we could have another block chained together and then chained into this machine and so on. So blockchain actually has a lot of real world uses to it. And the initial design of blockchain, you can actually see, was for self-defense and security type purposes. And these dates are accurate. You can check this if you don't believe my history, because this is the true history of blockchain. In May 2008, H. Simpson presented a concrete demonstration of blockchain for security purposes. There's later a computer version that became more popular, but this is the real first implementation of blockchain I've ever been able to find. All right, so that's the true history of blockchain. This isn't in order, what I'm giving you, by the way. So if you take those blockchains and you embed it, you end up with these hardware wallets. And the idea of that is that if you are trying to use Bitcoin, you have this issue that you have a computer and you want to send a Bitcoin from you on computer 1 to someone on computer 2. And rather than send it over the internet or store it on the computer directly, we use a hardware wallet. So the idea is that there's some secret that's required to send that Bitcoin. And that secret is only stored in this hardware wallet out here. And this hardware wallet, in this case, does this signing operation. So I'm going to send a Bitcoin to Josh, say, and it displays on my wallet, like, do you really want to send Josh 2 Bitcoin for services? And it says on the wallet, yes, you want to do this, and you hit it. And the wallet signs the request. So now I don't necessarily have to trust my computer isn't compromised. Because this external device is doing the signing and sending it off to computer 2. All right, so that's pretty good, pretty important, right? And the important thing is that we have some private key, so the private key is used in signing that we should never be able to recover. There's a bunch of different wallets. If you look at the market for this, you'll be amazed like how many there are. So I'm looking in particular at Trezor. Trezor is open source. This is nice because you can validate the code, you can modify it, you can see what the true effect is. And a lot of what I'm talking about applies to other things like embedded systems, outside of just pure Bitcoin wallets. Trezor did fix this problem, so I'm going to be talking about things, and if you have the latest firmware patch, it's already been fixed. So this has been previously dealt with. So in particular, on the Trezor devices, they have this recovery seed. So when you set up the wallet, it displays a bunch of words to you. This is called the recovery seed. And they really specifically say, if the device is lost, damaged, or stolen, you can use a recovery seed to restore access to the entire wallet. So all you need to do is you put the recovery seed into a new device. I should note you can optionally use a password protection for the recovery seed, which isn't on by default. But if you do that, that also eliminates the attack I'm presenting. Because what I'm recovering is just that sort of recovery seed there. So the Trezor itself, it looks like this. If you open it up, it has the STM32F2 inside it. So we already heard a little bit about that if you were at the chip.fail talk. So you can see there's not much to this. There's just a microcontroller, USB, some buttons, and a display, basically, and a clock. And getting the recovery seed, so this was presented at CCC by 2 people there and 1 person not here, Dimitri, Josh, and Thomas. So they basically were the first people to show a glitch attack on this device to actually get the recovery seed out. And this attack attacked the key when it was in SRAM. So when you do an update process, basically the key gets copied to SRAM. You could read the key out of SRAM by changing the code protection level, and then you had the private key. It requires physical access, but I mean, it's a pretty reliable glitch, so it's not like physical access was a serious problem. The only downside of this is maybe if you had physical access, it could leave some sort of obvious tampering. You'd have to either clone it or something like that to get rid of that. So what I was kind of curious is how else could this be done? And I got really curious about it because Dimitri was telling me, these 24 seeds, it's a string in RAM. So it's not like an encrypted binary and you get the dump and you say, ooh, what am I looking at? You literally are looking like a string in RAM. So it was sort of them doing this and him explaining how this worked to me that got me interested in what else I could do. So you start thinking about how else could you get that stuff out, right? So the SRAM is one thing, but they're actually stored in flash. So the real secure data is stored in flash, and it's copied to SRAM temporarily. So I was curious about getting it directly out of flash memory. So what we have here is this is the memory layout of the Trezor device. And this is not because I'm a great reverse engineer, not a reverse engineer at all, not even great. This is because it's open source. So you can just get the map when you compile it or in their documentation. So that's part of what makes this so handy, the fact that it's open source. And in particular, what you can see is that the recovery seed and the device pin are saved at this one block of memory up here. So you can see addresses, and they go from low to high. At a lower address, here is the bootloader. And in this bootloader, is there something that we could exploit to read out the recovery seed? And in particular, what I wanted to look at is some sort of buffer in the bootloader that's supposed to be read, but we could instead keep reading to read this sensitive data out really easily. And a prime target for this is USB. So USB, when you plug it in, it has something called USB descriptors. What these descriptors do is they send to the computer a description of, I am whatever, Bitcoin wallet, I am a keyboard, something like that. They're just big structs, effectively. And when the computer requests to read them, we have something called this W-length field. So the computer says, please send me up to 64K of descriptor, or up to 128 bytes of descriptor, whatever it is. The device will then send back, okay, the thing you're requesting is only 500 bytes or is only 16 bytes or whatever. So it only sends back the actual size of the descriptor, right, because it's just some chunk of memory. And the reason we have this field is that the computer could ask for less. So the design of USB by spec says, the computer could say, please give me 8 bytes only. I want 8 bytes of memory and that's it. And the device just sends back 8 bytes. So the device has to check this value to see if it should be, sending back even less data than it wants to send back. So how do we do this? In C, so if you take a look at the source code, in the USB source, and most USB stacks have something like this, you have this like min. So it says send the minimum of the length the user, the USB host stack sent in, or how big the actual structure is in memory, right? So it's whichever is smaller, that's how much data we're going to send back. And if we take a look at the assembly version of that, what you see is that the length of data is actually loaded first from the computer. So that the host value, the W length value, is loaded into register R1. It compares R1 with the value that it's the maximum size that it should be sending back. And if the computer requested too much, it then overwrites that. So if you were at chip.fail, you would have seen immediately, like, oh, okay, glitching is great for this, because we just saw how easy glitching could be done. And that's what we're going to look at, right? So if we could skip some of these checks or cause them to be performed incorrectly, all of a sudden this length value here is going to be used. And it's going to be used, and I can set that to FFFF. I can set it to like 65K of memory. Rather than do the glitch first, so as like a lazy first test, what I did is the firmware was compiled. So I took a Trezor wallet. I poorly, as you can see by the overheated LCD, desoldered the chip on it because it doesn't have JTAG enabled. You can't reload it as easily. And soldered a new chip on that, and then connected a debugger so that I could run the code. I could run the exact same code, except I could skip that check without actually doing any work at all. So I could skip the check, and I could confirm that normally it sends back 146 bytes, and when I do this skip, it sends back 65K. So I know this is, in theory, going to work if I can do that skip and get it to work. And inside that 65K, the other thing I could validate is that, that memory has originally the descriptors, and it just keeps going, and eventually it has this sensitive information, which here, it's one of these recovery seeds, so it's just a bunch of English strings, effectively, that store the private key. And there would be a pin and stuff in here, but I didn't set a pin on this example one. So how I'm going to induce a fault is using something called magnetic fault injection, electromagnetic fault injection. Basically what we have is like in a transformer or anything like that, you have a coil of wire. I have another coil of wire somewhere else. And if we pass current through that first loop, it's inducing current, it's inducing a voltage in this second loop. The changing magnetic field, so it's actually how fast that field changes, induces a voltage in another loop of wire. Well, if we put a chip here, right, like chips have things inside them that probably look kind of like wires. So if you induce it in a chip, there's going to be structures that will also generate voltages on the die. So we're basically just causing voltages to be induced on the die without actually needing physical contact. So coils, look something like this in real life. This additional thing in the middle here is a ferrite, so it's a material that's very conductive to magnetic fields, effectively. And this is what the setup looks like. So I have a device called Chip Shouter. This is a tool I make that does electromagnetic fault injection. We have a little tip. So this tip is a smaller coil right here. And we have a Trezor wallet here. And there's two screws that push on the buttons to force it to go into bootloader mode when it turns on. And you'll notice, so there's no hole or anything here, like these screws are just holding it down. This is going directly through the case of the device. So we don't actually need to modify the device in any meaningful way to get this to work. The other thing we need to know is when is that comparison happening? So I use the USB packets going into the device as a trigger. And in this case, we have a total beagle, a total phase beagle I'm using, which is a very nice USB analyzer that has some trigger capability. So I can set a trigger to say, hex C021 is going to trigger this device. The only downside to it is it's relatively expensive, so that's a problem I'm also solving in this presentation. But basically, I know, okay, when I send that request to the device, at some point very shortly after that request, it's going to process it, including doing that length check, so we can kind of sweep through and try to find where that length check is. So to do the full trigger with my original setup, I basically have a Beagle 480. This generates a single logic level trigger. I need to be able to sweep that trigger, so in my case I use this Chip Whisperer FPGA to adjust where the glitch is being inserted, so to sweep the glitch. It then generates a logic level signal to this EMFI device, Chip Shouter, and which then can trigger on the Trezor itself. We have a USB switch, so we need to hard cycle the device because it's often going to crash, as we'll see. So to replace these three devices, I made an open source tool called FiWhisper USB. So basically to replace the USB triggering, to replace the needing to sweep the glitch, and to replace the power cycling, There's basically this board that has a USB front end, so low speed, full speed, high speed, an FPGA, and a microcontroller for doing the download. It works a bit as a sniffer. There's no onboard memory, so the sniffing capability is a little more limited. And you can drive various fault injection boards. So here I'm using EMFI. If you use some chip.fail tools, you could sort of connect that in to actually insert the glitch itself. And you can see, so this is up now on GitHub, the design for it. It's a bit of an ongoing design, so you can take a look at it if you want. I have some PCBs here I'll talk about after. Yeah, so open source tool release, crash commercialization. So there is now, if you would like to just buy one instead of building it, I'm working on a crowd supply, so this is trying to make it available to everyone by getting enough people interested in it that might actually would like one of these devices. Okay, done. EMFI demo. All right. So I'll show you what EMFI kind of looks like. And okay, so this is a Trezor attached to the computer here. And you can see, right, this is how much I trust I'm not going to blow it up. There used to be one Bitcoin, because this was when I did the disclosure, they gave me a Bitcoin. But then I spent a bit on beer making equipment, so Bitcoin has a use, I discovered. Okay, so you see I disconnected it and it's disappeared. Anyway, let's take a look at that. Okay, so here's the Trezor. So right now it's connected to the computer, so it's asking for a PIN. And I'm going to turn on a fault injection tool. And basically this just discharges high voltage into this tip here. And then when I hold this button down, it's going to discharge. So let's get a better view, hopefully. That's not bad. What I want you to see is, right, I'm going to slowly come near it, and you'll see even without sort of, okay, there you go, right, like without touching it, I'm sort of a few millimeters away, you're able to cause weird stuff to happen. So this device has already, this is before the fix was done, right, they're trying to detect weird things like clock instability and other tricky business people are doing. So now you'd have to power cycle it, or you can just reset it with this. And so you see like unofficial firmware detected, right? So it's somehow corrupted the firmware check. Just reset it again, hard fault. So you'll trigger various errors on the device. So obviously this needs a trigger, so that's where the FI Whisperer part comes in. Ooh. You saw stack smashing detected, there you go, for 1 second. So they have this, they have various detection things put in. But it's pretty cool, right, that it's just done through the enclosure. Like let me reset it first. Okay. So if I kind of slowly come in, and you can just see the display. Okay, oops, there's a few different ones. But you can see, right, it's completely through the enclosure of the device. So that's the pretty cool thing about that, is that we're now talking about faults that don't need even like that level of physical access to be inserted. All right, gambling with Bitcoin. Okay, so this is bonus content. Since submitting, I'm giving a longer paper presented at Woot, so I present you bonus content as well. That's something that I discovered you could do as well. This is an open source FIDO2 authentication key. So how these keys work very briefly, you know, if you plug into your computer for two-factor auth or something like that, the token generates a public and private ECC key pair that's specific to every service it's registered with. So it's going to send the public key to, you know, whatever, Microsoft.com or something. It sends the public key to whatever service it's registered with. That service then stores that public key, and the private key is inside the device. Later, the website or app sends a challenge to the token. The token signs it with the private key it previously generated, and it now can send the response, and this app can verify. And these tokens are getting more and more popular, so there's like this password protection stuff going on now where you don't even have a password, you just have a token. And if you take a look at the token, so the solo key has in it a signing key, and if you kind of look a little bit up in memory, you'll see a hid descriptor. So in this case, this is an SRAM, and you know it's pretty nearby. And you also see the same min deal going on. And once again, you can verify first really easily that if you skip this check, it's going to dump up to 65K of memory. One thing I'll note is you might say, like, okay, Colin, but you're cheating because this is open source and you could see the memory layout and know where the ECC key is. It's not actually that bad. So normally, if you were attacking, say, like a real black box device, you could do this registration step with it. It would be like a new web app, and I hit the button and pretend to register. I get the public key for a private key that I don't care about, but I do this attack, I get the memory layout, and then it's very easy to check if a private key in a standard format is stored in memory that matches the public key. And then I know the location where it's storing the key and the format and stuff, and then I could attack a key I really care about. As a note too, this is one FIDO2 key or FIDO key. There's a bunch of different ones. There's a recent authentication level that's actually looking at protection against this. I think like YubiKey 5, for example, should be reaching these higher levels, so don't expect this to work on every device. Things aren't yet certified. This is fairly new, so if you go look for the tokens, what you might notice is you might say, like, oh, why do they all say level 1? Because it's fairly new. It's not because everything is super vulnerable to this. It's the particular token I look at had this issue, and they actually solved it in firmware release already. All right, yeah, how concerned should you be? So as part of fixing your code, you might question how concerned should you be? So is your device using USB? Obviously, and I'm talking about this specific attack. You can relax, don't worry about it. Is the sensitive data, it's using USB, but do you have sensitive data in the same memory space as USB? So for example, some authentication tokens have a separate USB memory controller and a separate secure element, so it's a little questionable if you could actually even read out of memory. So if not, again, this specific attack is irrelevant. Is it in the same memory space, but it's within 64K of any USB data? If not, you should be a little suspicious. There could be something going on, right? There could be a way to get this to work. But if it is, then you should be really concerned about this type of attack, and you should be looking at your USB stacks. And there's a whole bunch, like this min stuff is in basically all the USB stacks I looked at. Okay, so how to fix it? Why send back 64K of memory? No descriptors are that big. You can armor memory sections, so you can have like a sensitive memory section and an I/O memory section. And you can also move some memory layouts around. So if you move the memory layout around, you could try to make it so you can't read into sensitive data. This isn't as good if you have proper memory protection and stuff, because you might be able to still corrupt your way into it. The other thing is, for most of these attacks, right, like I'm relying on a dumb dump to tell me something, so it's either unencrypted or I can do this ECC private to public key trick. So the other thing is encrypting in place. Yeah, Trezor fixed it, Solo Key fixed it. Physical giveaways, takeaways first. Okay, so tamper-resistant enclosures aren't enough when discussing near physical attacks. These commercial EMFI tools exist and can be kind of purchased. If you're implementing a USB device, you should validate your response sizes, right? As a very, very basic fix, why send back 65K of data to a descriptor when no descriptor is ever bigger than like 200 or 300 bytes? And it's also useful for testing against EMFI or glitching in general. And the cool thing is that you can do a lot of testing with simulation, emulation, and through code review, right? So it's not always the case that you actually have to go and do the super advanced attack. You could see with the disassembly, I could basically look at the code, and with a debugger, I could do the same effects as that USB thing. Yeah, so physical giveaway, the last thing I promised. I brought some chip whispers too. Who wants chip whispers? I'm just going to throw them into the crowd. Okay, so there's 2 nanos, which are the new cheaper ones, and 1 good one. Okay, what are we going to do? We're just going to go this way, 1. We're going to go this way, 2. Watch out, they're like kind of heavy, and this way, 3. Oh, okay. Yes, now people are happy. And I have FI Whisper PCBs, so you can come find me. I brought 300 as opposed to Josh's 200, because I'm not as cheap as Josh. And if you have any questions, I think we're kind of going to be out of time here, so there's only a minute left. There's a paper with a little more details coming out as well, and I should have a blog post. I also do have, as I mentioned, the FI Whisper USB stuff is up now, so if you want to grab that, feel free to take a look at it, and if you want to build them. The PCBs have BGA, so I'm giving it to you, but good luck. Thanks very much.